So I think let's start with question 2. Unless there are really strong desires to do question 1. Question 1 is somewhat straightforward. You may get stuck on little parts of it, but I think it's something where there's a lot of value of you just trying to do it yourself. Like, try read the proof. It guides you through each of the steps that you need to do. And then on Thursday or Friday, I suggest you ask about what's going on in question 1. We can also do it today if we have time, but I think we should start with question 2. One question for all of you before we go. Have we done Cauchy sequences yet in lectures? When did we do it in lectures? Last week or today?
We started before he introduced it before.
Okay, last week.
Yeah.
Okay.
Just by the end of the session, I don't know, but
No, you started it today.
Okay, so we saw our definition of Cauchy sequences.
Yeah.
Okay, then I think I actually want to start there. So sorry, there is a question on Cauchy sequences on the tutorial, but I think that like typically each year there's a little bit of confusion of what's going on with Cauchy sequences. They're quite important. A lot of courses in real analysis actually start with Cauchy sequences before you do convergent sequences. But anyway. So let's start there. So I'm going to say some things about Cauchy sequences, and then we'll do stuff from tutorial 7. Okay, so just so that we're all on the same page, we have this idea. We're going to say, like, definition. Okay. AN is a Cauchy sequence. It's a Cauchy sequence. Is equivalent to saying that for all epsilon greater than 0, there exists an n, which is a natural number, such that for all n comma m, m greater than n implies that an minus am is less than epsilon. Okay? So that's just your definition. Okay? So you'll see some similarities with the definition of a convergent sequence, but it's not exactly the same, right? And so we need to talk about why. And we'll need to talk about what's the purpose of this. What is the picture that this is describing? And why do we care about it? Okay. And how does it relate to what we already know? So I'll just say here, roughly, this definition means that past a certain point in the sequence, all terms are arbitrarily close to each other.
So doesn't that mean convergent?
In fact, it does. Okay. And then you know, your next question is, so why have this? Like what's going on? Why do we care? Or you could ask another question, like, if it's not the same as it converging, then how? Like, or why? Like, So I give you this little kind of sentence or this little paragraph, and we just want to match it up to what's going on here. So we got comfortable, hopefully, with the epsilon kind of way of describing things, these formal definitions when we were talking about convergence. So this isn't too surprising, and there's some sort of argument about the terms in the sequence and the existence of some n that makes some inequality true. Okay. Do we see that roughly this inequality is describing the idea of different terms being close to each other? Okay. If we had to compare with convergence, we said that an goes to L was equivalent to saying that for all epsilon greater than 0, there exists an n such that little n greater than capital N implies that an minus L is less than epsilon. So the definition of convergence was saying something about this inequality, which was trying to capture the idea that the sequence is close to L, okay? Where L is the limit of the sequence. In this picture, for a Cauchy sequence, we're not saying that an is close to L, we're saying that an is close to am, where these are different terms in the sequence. So we're saying that different terms in the sequence are close to each other. Which terms in the sequence? All of the ones that are where this index is greater than some capital N. Okay? So that's kind of what I've written in this paragraph. Our definition says that past a certain point in the sequence, I'm counting down my sequence, I get to some point, all the terms are getting arbitrarily close to each other. And I really mean all of them. I mean that this first one past capital N is arbitrarily close to all of the other ones. All of those ones are arbitrarily close to that first one past capital N. If I pick any two that are much further past that capital N, they're arbitrarily close to each other. They're all closer to each other than epsilon. And then you know how that game works. You pick an epsilon, and then there exists an n that makes this true. And then you could pick a smaller epsilon, and there exists another capital N that makes this true. Okay. Now, if I had to draw kind of a picture, just to really kind of drive that point home, and I think the picture really does lead you to ask, how is this different from it converging? But we'll get to that. If I had to draw this picture, I might just represent it on a number line like this, just on a single real line. And I could say something like, well, maybe here is a capital N, okay? And then I could have a point like, maybe a capital N plus 1 is here, and maybe a capital N plus 2 is here. Okay, they don't have to be increasing or decreasing. They're all just kind of clustering together. Maybe A1 was over here. Maybe A2 was over there, and so on. But I get to some point where there's some A capital N, and then all of the other points in here are all going to go nearby. So this might be A capital N plus 10,000. Okay, this is getting messy, so I'm not sure exactly how you want to represent it when you're taking notes. But the idea is all of the other points are going to be in here. Somewhere clustering around here. They're all arbitrarily close to each other. Remember, this is really saying for all little n, little m that satisfy this inequality, the absolute value or the distance between those two things is going to be less than whatever epsilon you started with. Okay. So this is a bit messy, but this is sort of the way I think about it in my head. You might want to plot it maybe in a different way. You could try plot it on an axis like this, where n goes this way, and an is on this axis. But you would see the same kind of clustering. So you're maybe what you would see in this picture would be something like, here's A1, here's A2, here's A3, but at some point, maybe around here, all of the points are going to be nearby each other. And when nearby here, I mean on the y-axis. Okay, so I don't know which picture is more convincing, but that's the idea. All of the points, as you go to the tail end of the sequence, as you go to infinity, are close to each other, in some sense. And we make that's very precise by saying this definition. Okay? Any questions on this so far? Apart from the question about why is that different from convergence?
I think my question kind of overlaps with.
Okay, then let's talk about it.
The nature you told us that convergence does mean that the sequence is Cauchy, but then Cauchy doesn't always mean convergence.
Exactly.
It is for real numbers, I think.
So what's going on there?
Yes.
Yeah, definitely. That's exactly what we need to talk about. Yeah. So, yeah.
In the definition, you talk about an n and an m, but then when you explain, you say after a certain point. So what does that refer to, the n or the m?
So remember what I'm really thinking of is there's some variable here. Okay. Now it's maybe a bit funny that this n is appearing there and there and there. What I really mean is. I wish I had some more board space to draw. Perhaps maybe I can erase this paragraph because we've kind of written this down already. So, one way of sort of answering your question is, remember when I write something like an, I mean a list of numbers, but another way of thinking of that is I have some function from the natural numbers to the real numbers, okay? And what it does is it's like I have the natural numbers 1, 2, 3, 4, and so on, maybe up to some capital N, and so on, and it assigns a real number to each of them, A1, A2, A3, right? A4, AN. So that's what a sequence is, right? And it must be infinite. So when I'm writing these little ANs and little AMs, I'm just saying some value, some value of that variable, some input into this function. I'm not sure if we're getting closer to answering your question. Are you uncomfortable with the fact that I've called the sequence an, and then there's an n, and a little n, and a little m?
Yeah, and then after some point.
So the sum point references this capital N. Okay. So and remember, capital N really is a natural number, and so I can always plug in a natural number into my function or into my sequence. I can ask which term in the sequence corresponds to that capital N. Okay. Because I have the first term in my sequence, that corresponds to 1. The second term in my sequence corresponds to 2. So I can count up to the capital N term in my sequence. And then what this definition is telling you is that if I go past those terms, this inequality is true. And how is that being represented here? It's saying pick any two natural numbers, any two. Really doesn't matter what they are. Any two natural numbers that are bigger than this natural number, plug them into this function, or in other words, pick that term in the sequence where I count up to the nth term and the mth term, and then this inequality will be true. Okay. And another way of thinking that is saying that there is a capital N term, and then I'm looking at all the terms past that. That's what this is trying to do. Any other questions before I go on to like the sort of bigger picture? Okay, so. So, we'll say something like this. How is Cauchy different from converging. Okay? And hopefully this kind of answers why should we care about Cauchy sequences. Okay. Well, and you see why I'm asking that question, right? Because if I tell you that past a certain point in the sequence, all of the terms are really close to each other, doesn't that sound like converging? Isn't that what converging is? They're close to something. Well, non-rigorous answer. Okay. A sequence being Cauchy allows us to talk about the sequence converging when the limit may or may not be in the space. Now, do I want to say, maybe let's say in the set. Let's just say it that way. In the set. That the sequence comes from, maybe? So let's discuss this. This is for your notes. We'll just write it out carefully. So I'm saying, what is one way to think of it? Sort of non-rigorous answer. I'm not going to focus too much on like the literal truth of what's going on, but this is the rough way to think about it. A sequence being Cauchy helps us talk about it converging, even in the case when the limit is not in the set where the terms of the sequence came from. So your very basic example, let's just give you that example. Yeah.
So we use the Cauchy thing if we don't know we don't know the limit. So we try to use the Cauchy theorem, or whatever it's called, to try and prove the convergence of it.
That's sort of like it. I think that could be true. Like, so it depends on how sort of pragmatic or how practical you want it to be. So I'm not sure how often it is the case that someone like sits down and says like, let me find out if this thing's Cauchy, and if I do, then I can do something with it, in terms of finding its limit. That does happen. So, but I think like, let's say it this way. The situation is like this. You might find a sequence of numbers that it behaves in a way that seems like it's converging. And yet, the thing that it's converging to is not in the space that all those numbers come from. And we're going to see like the simplest example of that, I'll write it down, but is 1 over n. So if I wanted to ask, I'm just studying Q, pretend I live in a universe where I only know Q, I only know the rational numbers. I've never learned about anything else. And then I study the sequence, sorry, 1 over n is a bad example, but we saw a sequence that converges to square root of 2, okay, in the real numbers. Okay, and I'll write that down. But you could have this sequence of rational numbers that converges to a number that is not a rational number. That's been a key idea that we brought up earlier. And so you'd say, like, if you studied this sequence just with the tools available to you, in other words, just like writing down to very big terms these rational numbers, you would see them getting closer and closer to each other. And you would ask, like, what can I write down to, like, describe that? And what you might come up with is saying that this definition of being a Cauchy sequence. Okay? So you want to describe this idea that all the terms are close to each other. You wouldn't be able to write down the definition of it being a convergence sequence, because you'd have to say something like, there's this L that it converges to, but there is no L in the rational numbers. There's no, you haven't discovered the square root of 2 yet. So that's sort of like the big picture story, and actually historically kind of how it goes. Yeah. So that's kind of the situation. I just want to search one thing to show you. Is that okay out there? Or, okay, maybe this is a really good one. So example. Okay. Suppose we only know about Q. And we study AN defined as 1 plus 1 over n to the n. Okay? So this is just a sequence where every term in the sequence is a rational number, right? For every n, every natural number I put in here, I'm going to get a rational number for every term. If we know about R, we have AN converging to E. Okay? But if we only know Q, all we might discover is that AN is Cauchy. So that's the idea. We could write down this sequence of rational numbers, and we could really generate them for a long time and look at them and see, oh, okay, they're getting really close to each other. But we would struggle to kind of say more than that unless we have this number, which is just not a rational number. Yeah?
So we try and maybe try to find if AN is bounded then?
Yeah. You could say something like that. You would find out that it is bounded. It definitely is. But that wouldn't be enough to describe this behavior that you observe, right? Because we know that every convergent sequence is bounded, but not every bounded sequence is convergent, right?
But often we know that it's Cauchy, and then we try and...
Then you could prove it's bounded. Every Cauchy sequence is bounded.
And then obviously with the bounded thing, we're using... Okay,
yeah, unfortunately it wouldn't add more to you.
okay.
Yeah, it would be something that's true, but it wouldn't take you to this idea of it converging to a particular number.
Oh,
Okay. So now, we get to like probably the most interesting part of the story. But do we see what I'm saying here? So this is just a rough sort of way of thinking, how should I think about Cauchy sequences? Well, it's describing that as the sequence goes towards infinity, all the terms get close to each other, they cluster, but it allows me to talk about them doing that. They kind of have a converging behavior, but I didn't have to mention the limit. And why would that be useful? It could be useful if that number L is not actually part of my space. In fact, I may not have discovered it yet. I may not have invented it yet. Okay? So, the most interesting part of the story now is really to ask, like, what are the real numbers? And I don't know if this has been said in lectures or earlier, but one way of actually constructing the real numbers, to say that you really get all of the real numbers, is to take every single Cauchy sequence of rational numbers, and then if you find that those Cauchy sequences are converging to some point that is not a rational number, you add those points in to the set. So you start with all the rational numbers, you figure out all the sequences that you can make that are Cauchy sequences. You know that Cauchy means that they get arbitrarily close to each other. Sometimes they will converge to rational numbers. Sometimes they will converge to numbers that are not rational numbers, okay? And you add those points into your set. And so when you have the rational numbers plus all of the points that the Cauchy sequences converge to, you get the real numbers. And that's actually a big part of why people care about Cauchy sequences. But I'll just write that down. Okay, maybe we're going to switch to yellow. So I don't know if I should. Notice we'll say it this way, Q is incomplete in some sense because there exist Cauchy sequences that do not converge to rational numbers. Okay? And sometimes people say this like, there are holes if you tried to only represent the rational numbers as a number line. So this is just like a long paragraph that describes an idea that I think we've kind of already talked about in the course, but it just appears again here. Is this idea that if you only had the rational numbers and you tried to kind of represent it as a number line, you would kind of have holes. We know that there exist these numbers that are just not rational numbers. We can find these sequences of rational numbers that get arbitrarily close to certain numbers that are not rational numbers, the irrational numbers, right? And so So R defined as Q plus the limits of all Cauchy sequences in Q. Okay? So that's actually one way of just saying, where does R come from? You want to describe the idea of things converging in a rigorous way. So you study these things called Cauchy sequences that kind of have a behavior like they're converging. In other words, all of the terms eventually get close to each other. And then you find out that those sequences have an interesting property. Sometimes they converge to rational numbers. Sometimes they converge to numbers that are not rational numbers.
Don't you mean the limits of Cauchy sequences which are not irrational?
No, are in so I think I worry maybe I phrased that not exactly the best way, but I mean what's written there in the sense that when I say a Cauchy sequence in Q, I mean that all of the terms in the sequence come from Q. The limit might not come from Q, it might.
Oh, the limits.
Because remember, Cauchy sequence is defined without mentioning a limit. So when I say a Cauchy sequence in R, I mean all of the terms in the sequence are from R.
Yeah.
If I say a Cauchy sequence in Q, all of the terms in the sequence are from Q. You could do it another. You could say Cauchy sequence in the integers. You could say Cauchy, but those are less interesting. Is that cool? No?
I'm so confused. Because he's saying R is defined as rationals plus the limits of all sequences in rationals. So the limits are not in the not necessarily.
So not
in the
necessarily,
rational.
exactly. We saw an example
But-
right here.
Yeah, okay. So the limits are not
Not necessarily. So maybe the order, you could rewrite this sentence if it's a way that makes more sense to you. So maybe I just ordered this, but I mean the limits of a certain type of sequence. What type of sequence? A Cauchy sequence in Q.
Okay.
What do I mean by Cauchy sequence in Q? All the terms are rational. Is that cool? Yeah. You had a question?
I have a similar question.
Mm-hmm.
So, by this last statement, you mean every irrational number can be written in terms of Cauchy sequence?
Exactly. And that's quite interesting, right? Because you could also ask a question like, are there more? Like when we build the real numbers, you're like, oh, let me take the rational numbers and let me take the irrational numbers and kind of put them together. But did you notice when we said what is an irrational number? It's a real number that isn't rational. And that's not really a reasonable way to build R. Because how can I tell you that, well, I want the rational numbers, which we understand well, like we can write down what they are carefully. And then I tell you I also want to add in this group of numbers that are all the real numbers that are not rational. And then I tell you that that whole thing together is R. But how did we know what R was in the first place to be able to like delete the rational numbers and then say that the irrational numbers are whatever is left? Do you see? So you ask a very reasonable question, is like, can I get all the irrational numbers as the limits of Cauchy sequences of rational numbers? And the answer is absolutely yes. And that may seem a little bit funny, but perhaps I could convince you by just saying, think about decimals. Like, every single real number can be written as some sort of integer part plus some decimal. Okay? That decimal part might be infinite, it might be finite, it might repeat, it might not repeat. Okay? And do you kind of agree that if it's finite, it's a rational number? Okay? Yes. Because I can just write it as sort of like, you know, let's say the decimal part is like 0.23. Okay? What is that? That's 2 over 10 plus 3 over 100. Right? So every decimal number that is finite is a rational number. Okay? And so then when I say that we can get every irrational number as the kind of limit of a Cauchy sequence of rational numbers, one way of saying that is just saying I could just, as long as I add enough decimal places and I modify those numbers correctly, I could eventually get arbitrarily close to that number. And what do we mean by close? The whole epsilon delta thing. Okay. And that's not too crazy when we think about it that way. But you can prove this all rigorously. It's not really the focus of this course, but it's true. Yeah. And actually, they refer to this idea as the idea of completing the rational numbers. You take all the Cauchy sequences, and then you add in all their limits into the rational numbers, and you get the real numbers. And you might ask yourself, should I go bigger? Is there some bigger thing? Or should I go small, or something like that? No, you can prove that by doing this, you get kind of a unique object, and you've kind of completed the real line. You've filled up all those holes that the rational numbers could converge to. Yeah, but anyway, we're not so focused on all of the rigor behind that, but that's just the reason. It's useful to have a picture in your head. Why should I care about this? Let's see, eraser. And then there's one other key fact. So key fact a sequence AN is Cauchy perhaps I'll write it this way just so that there's no confusion. A sequence AN where the terms come from, sorry, I apologize for your notes. I'm gonna, sorry. We're gonna have to rephrase this. Let's say it this way. So sorry, just to say it in words. So what I want to say is that sequences are, if the terms come from R, it converges something in R, it's Cauchy if and only if it converges. Okay, and I just want to distinguish that from the previous case where we were forcing ourselves to only talk about sequences in Q. So let's say, I think you'll know what I mean if I write it this way. So a sequence is Cauchy, sequence AN is Cauchy say over R, and I'll write it's equivalent to saying that AN converges. Okay. Maybe that's enough to just capture the idea. Okay. And so if you want to remember which is the one that sometimes doesn't happen, from the story we've been telling, we see that in some sets of numbers, Cauchy sequences do not converge. Okay? In fact, the rational numbers are a prototypical example. So sometimes Cauchy sequences do not converge. What do we mean by that? We mean the number that they're getting close to is not in the set. Okay? And a key example of that is the rationals. Okay? In the real numbers are special because all of the Cauchy sequences converge to some real number, and all of the convergent sequences are Cauchy. Okay? And so maybe I'll just add that just because it's the kind of first or second time we're seeing this, let's just add that very carefully. So, converging implies Cauchy always for some sets of numbers, Cauchy does not imply convergence. E.g. Q. Okay, so this is like for your multiple choice questions where they ask you. You don't want to just memorize it, you want to have an easy way to remember why it would be true. Why is it true? You can always make Cauchy sequences. You can write down that definition. If you look carefully at the definition, you can always write down that definition for any set of numbers, whether they're rational, integers, real numbers, complex numbers. But in the definition of convergent, we had to write down L. We had to say there's some L such that the absolute value of an minus L is less than epsilon, and that L just simply does not exist some of the time if you're not in the real numbers. If you're in the rational numbers, I erased it already, but you will have sequences that converge to numbers that are not in the rational numbers. So you cannot say that there exists that L.
I don't know actually this definition, but when they say that this Cauchy only implies convergent in the real numbers, I thought maybe when it doesn't imply, they mean non-real. As in like everything in real, including the rationals, would be like the Cauchy would imply convergent, whereas it's non-real.
Non-real being like imaginary.
Yeah. Yes.
Oh, I see. Yeah. So this is the situation.
Imaginary numbers and real analysis.
Yeah. No, not yet. Although much of what we're doing is similar if you were to do complex analysis. You just need to be careful of what you mean by absolute value. You mean the norm. But anyway. So, you know, you'd be surprised if you look at complex analysis ever, you'll see that almost all the definitions we're writing are very similar. Just need to be careful what we mean by close to, because a lot of this is all about the notion of being close to. We want sequences to be close to numbers, and so on. But anyway, so this is the way to remember it. If you have this backstory, it's much easier to remember than if you just memorize which of these is true, right? The backstory is we actually built the real numbers by taking all the Cauchy sequence of rational numbers, and then looking at what their limits seem to be, and defining the real numbers to be all of the rational numbers plus all of those limits. And yeah, you can go into that more, but not really our focus. Okay, so I think that's enough. Now really what's important is to do examples. So just to make sure that we really understood what's going on with the definition of Cauchy. This proof, by the way, highly valuable. Strongly recommend. It's not too many steps. It will be in the textbook, I imagine. I'll maybe send out an announcement, or maybe you've got it in your lecture notes, I'm not sure. But this proof is not too long, and it involves key steps that get used in lots of other proofs and lots of other ideas that we do. So I strongly recommend on your own work through and see, can I take a Cauchy sequence? So I write down the definition of it being Cauchy, and using that alone, can I show that that sequence converges? And then, can I take a convergent sequence? I write down the definition. And can I manipulate the inequalities to show that it's Cauchy? So I'm going to recommend that you look through that on your own. We may do that next time, if there are still questions on that. Okay? But for now, I think we'll do some examples. Any more questions on this? Okay. So now we're going to go to TUT 7. And I think let's start with question 3, because that's the one that involves Cauchy sequences. So we'll do that, and then if there's time, we'll do question 2, and go from there. So, what's the right? Okay. So we're on TUT 7, question 3. Okay. And they say, let AN converge to a half. So you just have some sequence. They don't tell you what it is at all, but they tell you that it converges to a half. Sorry, let's just be consistent. They say AK. And they define a new sequence, BK, which is, and I think it was 1 over 1 minus? Yeah. 1 over 1 minus AK. Okay? And they say, prove from the definition, that BK is Cauchy. I think? Yes. Okay. So this is a good exercise, right? We have to immediately use our definition of Cauchy. So let's just write down carefully what we want to show, or what we want to prove. I want to prove that for all epsilon greater than 0, there exists a capital N such that n comma m greater than n implies that bn minus bm is less than epsilon. Okay. So we just write down the definition. And much like the thing we did when we were practicing proving that sequences converge by the definition, we have to follow a similar strategy. We've got to find this capital N, or show that such a capital N exists, making this inequality true. So what do we do first? We sub into the inequality, because we want to simplify this and change it into something that's easier to attack. Okay? So we start off rough, try to figure out what's true, then we prove it. Okay, so I just plug into the inequality. This has an n, so I just put in n where I see k. 1 over 1 minus a n minus 1 over 1 minus a m. Okay? That's what I'm looking to show. Well, I'm looking to show the existence of a capital N that makes this true. Okay. So I think we can all guess what we're going to do next is just kind of simplify this a bit, find common denominator, do all that, see if we can get it into just a slightly different looking form. And you can also guess that, like those kind of questions you've done before, where they said something like an converges to 4, prove that 1 over an converges to 1 over 4, we're going to have to eventually use the fact that ak converges to do this, because we have this inequality that involves the a's. So we're going to have to use what we know about the a's. But first, let's just simplify this a bit, or rearrange it a bit. So we just do common denominator. Okay? So what I see is this is equivalent to saying that I'm going to have an minus am over 1 minus an, 1 minus an. And I want that to be less than epsilon. Okay? And we can just check, why did that work? I multiplied this times the top. I multiplied this times the top, but I have a minus sign. So I have a 1 up here, and I have a minus 1, so those are gone. I have a minus am right there, and I have a plus an there. Okay. So if we just, it might look a little fast, but if you just check, this really is equal to that. Okay. So now we're starting to see something a little familiar to what we were doing with convergent sequences. We have some stuff in the denominator, so we're going to have to deal with that. And we have some stuff in the numerator. So we're probably going to have one of those arguments where we have like an n1 that allows us to handle the numerator, and an n2 that allows us to handle the denominator, and then we take the max and so on. So that's what I'm seeing here, and that's a general strategy when you see something in the denominator and something in the numerator. Okay. Now the numerator looks a little bit funny though. In the past we would have just had like an minus 4, and we would have just used the fact that an converges to work with that. But now we have this n and this m. It actually, the numerator is looking like saying something about being Cauchy. That's your hint. If you have two different variables or two different indexes, you're probably going to have to use something to do with the definition of it being Cauchy. Okay? Because Cauchy is the one that involves two different indices, right? Now, it's going to depend a little bit on what they allow you to do on how I'm going to attack this. Because they've told us that AK converges. Now, if they're happy with us just saying, well, we know from lectures that AK converges, so therefore it's Cauchy, then I already have a way of handling the numerator, okay? If they're not happy with me using that, I'm going to have to directly prove from the definition that that thing converging to a half, AK converging to a half, means that AK is Cauchy, okay? So which one do we want to see? Maybe the longer one? Yeah. My suspicion is, in general, you will not need to do this, but I think it's worth seeing it, okay? In general, we know the rule, if you've seen it in lectures, you're allowed to use it. So you would say, from lectures, I know that that converges, so therefore it's Cauchy, so therefore I can start treating the numerator, and then all you have to do is figure out the argument for the denominator. But let's just do it the long way, okay? So, let's make a little comment. We need to treat the numerator and denominator separately. Okay? So numerator okay. So I know, so now I want to know what to do. It's always useful to write down what I already know. The only piece of information that I know at this point that I haven't used yet is that AK converges to a half. So I know that I have something available to me that looks kind of like this for some epsilon. Okay? And my question is, how can I relate this numerator to that? Okay? I might just write a little comment here, is available to me. Is available to me. Okay? Again, we're working roughly right now. We're just asking what kind of things are floating around. So how am I going to relate this numerator to that kind of inequality? Well, I want to start including stuff that looks like a with some variable minus a half. So what I'm going to do is I'm going to write an minus a half, okay, because I want that. But if I want to write down something that's equal to the numerator, I also have to add a half. And then I'll write a minus an. So this is equal to the numerator. Okay. And then you'll just see, well, that's really equal to an minus a half minus am minus a half. Okay, I just factored out a minus sign. Just write maybe up in the corner here what we were dealing with. It was an minus am over 1 minus an 1 minus am less than epsilon. Okay. So you can kind of guess what I'm going to do now. I've rewritten that numerator to involve something that looks like the definition for convergence. Okay. So we're going to say triangle inequality, that line continuing here, is less than or equal to an minus a half plus am minus a half. And then we agree from here that I would find a capital N so that I can make this less than epsilon or epsilon times some constant. Okay. If I wrote it out really formally, I could say, well, maybe we'll come back to that when we write out a formal proof. Sorry, but do we agree we've kind of got the ingredients now that we could bound this by some epsilon? Okay, and we'll be a little more careful on how we do it exactly when we write out our formal proof. But the key step was saying, how can I rewrite the numerator to involve something I already know? And that's the idea. You might ask, how did I know to do this? Well, it's sort of like I said, it's like you know that you need an minus a half, so you should just write that down and then see what other things you need to do to make that work. And in this case, adding a half and factoring out a minus sign was enough. But a lot of this just comes from experience. It's like you need to do lots of examples, and you'll see this particular technique where you add and subtract the right number over and over again. So it's not the most magical thing, but it's a little bit hard to think of the first time. Okay, so what's left to do is we have to deal with the denominator. We need to sketch out a way of treating the denominator. Okay. Okay. And this is going to be really similar to what we did in the past, where we had terms in the sequence in the denominator. So what I'm going to do is I'm going to say that I know I have something like mod a n minus a half less than some C. Okay, I know that's available to me, that kind of inequality. Is available. Okay. And the question is, how can I make that look like 1 divided by 1 minus an? Okay. So this is equivalent to saying that minus c plus a half is less than an is less than c plus a half. Okay. So this is that old strategy of like, I have this, so let me undo the absolute value by just writing an minus a half less than c, and an minus a half is greater than minus c, and then I just add a half to the whole inequality. Is everyone happy with how I went from here to here? Okay. And then we look at what we want to make this look like. Again, we're chasing 1 divided by 1 minus an. So what I need is a 1 minus an here. So it's going to multiply by minus 1. By minus 1 through the whole thing. So I have c minus a half is greater than minus an, which is greater than minus c minus a half. Okay. And I did write it up here. Remember, we don't want just minus an, we want 1 minus an. So I'm just going to add 1 across the whole thing. So I have, and I'm going to just write things a bit more logically. I'm going to flip it over here. So when I add 1 here, I get c plus 3 over 2, or sorry, c plus a half. Okay, and that's greater than 1 minus an, which is greater than, I add 1 here, I get a half minus c. Okay. And then we just get to that old question of like, what should I choose for c? Remember, I want 1 divided by 1 minus an to be less than something. So I want to kind of divide this over and have 1 divided by this be less than something. So I need to move this over here, and in order to do that, I really want this to be positive. Okay. So do we agree that this implies that 1 minus 1 over an is less than 1 divided by a half minus c if a half minus c is greater than 0. Okay, that's sort of what I'm saying. This is the thing I care about because it appears up there. It might be a little small to see, but if you look back in your notes, we had 1 divided by 1 minus an in our expression. So I have that here. I can divide by it. I can divide by this and keep the inequality doing what I want as long as this thing I divided by is greater than 0. Okay, so what should we choose c to be? If we want this to be greater than 0. Probably just choose a quarter, something like that. Anything like that. We have some freedom. We can buy it. So we could choose c to be a quarter. I wonder, is there no? So we'll write here. So choose C equals 1 over 4. Okay. And then kind of all together, there exists a capital N such that 1 divided by 1 minus an is less than 4 for all little n greater than that capital N. That's what we're learning. Okay, so I went back to the definition and I said all of this could be concluded from using the definition that an converges to a half. Okay, are we happy with that? This is like the more subtle part of the argument, but it's similar to what we've done in the past, right? It's pretty much the same thing that we've done in the past. So I'm going to start putting all the puzzle pieces together now. And then, so we'd say now formal proof. You don't need to write formal, but I write it just so that we kind of have a break in our notes where we're going. You can just write proof when you're doing this. Or if it helps you, can write formal proof. So we start out and we say, suppose we are given epsilon greater than 0. Okay? Okay. So and we could just write AK converges to a half implies there exists an N1 such that N comma M greater than N1 implies 1 over 1 minus A n less than 4 and 1 over 1 minus AM less than 4. Actually, let me just erase that quickly, sorry. You don't need the second one. We're going to use it, but you'll see why it's logically fine just to say this. Remember, I'm just saying any variable, any index that's greater than n1 implies that if I put that index in here, this is true. So we don't need to say it separately for n. Okay, but we'll see how that fits together. Okay, so that's treating the denominator parts. We also have that, so this would be, we could write like even a 1 here if we wanted to, 2. AK goes to a half implies there exists an N2 such that N greater than N2 implies A n minus a half less than, and we'll just think about what we want to choose. So let's say, I think we want epsilon over 32, but we'll see. This number I'm just doing to be fancy. Like, you know, when you write these proofs, you don't have to focus too much on what you multiply epsilon by. We all agree that as long as you show it's bounded by some epsilon times some constant, that's enough to do everything. We've said that in lectures. Okay, okay, so we have these two facts. We've shown them in our rough work. So now let's prove everything we wanted to show. So I would write then for all n comma m greater than n, which we'll define as the max of n1 and n2, both conditions hold, right? We're happy with that kind of argument already. And that means I can write this whole inequality chain where I had bn minus bn. Okay, this was my Cauchy condition on B. We showed that was equal to an minus am over 1 minus am n 1 minus am. Okay. And that's going to be using the fact that n and m are both bigger than that thing. That capital N means that I can use the first condition on this and this. So that's less than 16 times an minus am. Okay. It's maybe a little bit subtle, so I know that this whole thing is less than 16 times just the numerator, because I know that I wish I could draw another color. I know that this part times this thing is less than 4 times. Are we happy with where the 16 came from? I applied that inequality to this to get a factor of 4, and then I applied it to this to get a factor of 4. Okay, I can write it in 2 steps if we want as well. Does anyone want it written in 2 steps? 2 steps, no problem. Always better to use more steps at the start and fewer steps later. Okay, so we would just say it's less than 4 times an minus am divided by 1 minus am. Okay, and I'll write here why? Because, let me actually write it in a different color. This inequality is because n is greater than n1. Okay? Do you see that? And then this is less than 16 times an minus am. Why? Because m, is greater than n1. Right? Because we're looking at all the n's and m's that are bigger than n, capital N, which is the max of these. Okay. Are we happy so far with those 2 inequalities? Okay. So we were just using condition 1 twice. Okay? And then we know that that's less than, oops, wrong color, less than 16 times mod an minus a half plus 16 times mod am minus a half. Okay? That was that argument earlier where we saw we could add and subtract a half inside of here and then use the triangle inequality. So I'll just write here plus or minus a half and triangle inequality. That's how we got this step. Okay? And then this is going to be less than epsilon over 2 plus epsilon over 2 equals epsilon. And this was because n is greater than n2 and m is greater than n2. Are you happy with that step? Okay. And so then we just look at what did we actually prove with this sort of like long chain of inequalities. We showed that given some epsilon greater than 0, the fact that AK converges to a half led to this whole long argument that basically there's some n, capital N, that does exist because these two exist, and such that whenever n and little m are greater than that, we have that Bn minus Bm is less than epsilon. And that's the Cauchy condition. Okay. And if you wanted to, you could say, so B or BK, whatever, you can always relabel, is Cauchy. It's quite involved. It seems long. You do it more on your own and it'll go much faster because we really did show each individual step. But it's quite directly related to things we've already used, and we just want to not get tripped up by having two variables. That's our goal. And then similarly, when you're facing a question, as I was saying kind of earlier, and they ask you, or they show you an object like this, seeing two variables telegraphs to you that maybe you have to consider the fact that it's Cauchy, right? You don't see these two indices when you have a converging sequence. But okay, so that was part A of the question. That was the really long, rigorous, careful way to do part A of question 3 on TOT 7. Question B asked us to just prove directly from the definition that the limit of BK is 2. Okay. Now we've done lots of examples like that. I'd be happy to do it next time, but I'm going to suggest you do it on your own or check the solutions or do it in the tutorial on Thursday or Friday, because that's not using anything new that we've done. But I still recommend you do it. The more times you do it. If you feel like it's too easy for you, then do it in like 30 seconds. If you can't do it in 30 seconds, then maybe it's not too easy. You do it, feel better on the next test or the next exam. Okay, so perhaps we can talk quickly about question 2. We have about 5 minutes left. Okay. But this was just like a long primer on Cauchy sequences. Is anyone still writing? I don't want to erase while you're writing. Maybe I'll leave this up and erase down here. So question 2 is more focusing on subsequences, which is something we haven't really discussed in this workshop. So we're all happy with what subsequences are. We're really just saying that I have an infinite list of numbers, that's my sequence, and if I take some sub-list of that number, of those numbers, in other words, I just take some of them, as long as that's also an infinite list of numbers, then that's a subsequence, okay? And the simplest one would be like, I write out my infinite list of numbers, which is my sequence, and then I just take the even ones. I don't mean the numbers that are even in there, I mean I take the second term in the list, the fourth term, the sixth, the eighth, all the way to that infinite list of them, that would be a subsequence. Okay? I could take the odd ones, but there are other subsequences, of course. Any infinite list of numbers that is contained in the original list is a subsequence. They must be infinite. Because if it's not infinite, then it's not a sequence. Okay? So a subsequence is a sequence. Okay? Anyway, so they ask us, they say, give an example where give an example AK where A2K converges to some L and A2K minus 1 converges to some L1 and L2, but L1 is not equal to L2. Okay? So sort of writing this out, this is like the really quick sort of fancy way of writing it. What am I saying? I'm saying that I have this list of numbers and the second, fourth, sixth, eighth, all the even terms converge to something, some number L1, and the odd terms converge to some number L2, but those two numbers are required not to be equal. Okay? And so what's an example we could do that? Negative 1 to the power n, that's good. So AK defined as negative 1 to the power n, or I should say an, sorry. Okay, and we just write that out. What does that look like? In other words, I have this list where the first term is minus 1, then minus 1, then 1, then minus 1, then 1, and so on. Okay? And then A2K, is just the list of the even terms, or the even indexes. So that's just 1, 1, 1. Okay? And then A2K minus 1 is just equal to minus 1, minus 1, minus 1. Okay? So that works, right? So what were we asked to do? We were asked to find a subsequence of the even terms that converges to some number. The subsequence of the odd terms converges to a different number, and that's definitely happening here. We have this sequence AN that goes minus 1, 1, minus 1, 1, so on. The even terms are converging to 1 because it's just a constant sequence. The odd terms are converging to minus 1 because it's just a constant sequence. But, you know, those two limits are not equal, which is what we were asked to do here. Is anyone unhappy or unsure because we went a little fast? But said in fancy words, we just said, or in more formal language, find a sequence such that it has two convergent subsequences that do not converge to the same limit. Now, the next question says, give an example with 3 different limits. And I think we could all do that quite quickly. I don't think I'll write that out, but you could just make a sequence that is like minus 1, 1, 0, minus 1, 1, 0, minus 1, 1, 0. Okay? That will definitely have 3 different subsequences that converge to 3 different limits that are not equal. And you could do more fancy things. You could say like, just very quickly, because they might give you a question like, they might say something like, find a sequence such that